Hello, I think I am audible. Yeah, so hello everyone, welcome to this problem solving session. So we'll start with the session today. So this is the extra session for clearing the doubts. So if you have any doubt related to the content present, uh, you can ask, or otherwise I will solve some of the design problem which were covered in the in the mostly every week there was some design problems which were given the solution also for those solution were also provided, but I will try to explain in my way and like different compared to the solution, or is it related to the solution which is already there in the class. But these problems are quite an extensive and in comparison to the uh, problem solving for each of the weeks, it those are more of a objective type problems, but these are more like design problems or so let's just move to uh, problem solving question. Till then, if you have any doubt, you can ask now. I'll pause for some time. So then basically, otherwise we will start the session just now. So in this basically one problem. We need to design a three section. So three section Chebyshev a transformer to match a uh, 150 ohm load to a 75 ohm transmission line. So basically, the load resistance is 75 ohm. So basically, you did need to design a, let's say these are three lines. You need to design a three section line which matches to this load. So, so this is one section, this is other section, this is, and here you need to find Z in. Also, this is the n equals to you can define the node. So this is at the load side. So gamma 0 you can define as ZL minus. Uh, so basically, you need to find the each of the this gamma 1, gamma 2, gamma 3. So of the each of the lines. So that you can just at each of the cross section, basically you need to find the this is basically equals to the, if your this characteristic impedance is Z1, if you call it no, let's just call gamma naught, gamma 1, gamma 2, and then this is Z naught, Z1, Z2. So this character, then basically gamma naught is basically equals to Z L minus Z naught divided by ZL plus Z naught. And basically, if you find out the value of gamma 1, gamma 2, gamma 3, Z1, Z2, Z3, Z naught, Z1, Z2, then basically you can just arrive at the, then basically your your impedance transformer or matching network is defined. And also we need to take this Chebyshev polynomial for designing this this circuit. So let's just get started. So the reflection coefficient gamma of in terms of electrical path length for a different section lines is given by this. So if you consider equal the line of these, each line is equal, so you can write gamma in terms of theta, and which is equal to 2 times exponential of minus j n theta times gamma naught cos n theta plus gamma 1 cos n minus 2 theta plus so on gamma n cos n minus 2n theta. So this is your polynomial for and this is equals to your Chebyshev uh, 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 equals to the Chebyshev polynomial, which is equals to the gamma m exponential of minus j n theta Tn sec theta m cos of theta. So this is your Chebyshev. So this is the Chebyshev polynomial. So and n is the number of sections. So basically, in our case, n is basically equals to 3, which is we need to design the 3-section line, and uh, gamma L is given as like the load is given as 150 ohm, 150 ohm, and here the at the input it's like 75 ohm line is there. So then basically so now we can define this and a ripple pass band. So basically this reflection coefficient will be this, and gamma m, which tolerance limit you can set, this is 0.05. So this much ripple you can tolerate. So basically for n equals to 3, so we will put in this equation n equals to 3. So then it will become gamma of theta will become uh, gamma of theta will become uh, exponential of 2 times exponential minus j3 theta uh, gamma naught cos of 3 theta plus so this 3 minus 2 so gamma 1 cos of 2 theta, so this will become cos of theta, right? And then this other term will be 0. So this is and that is equals to other term will be 0, then that is equals to uh, gamma m exponential of minus j times 3 theta Tn sec of theta m cos of theta. So that basically now so for n equals to 3, so you can define your for n equals to 3, you can define your Chebyshev polynomial. If you expand this Chebyshev polynomial, this will become gamma m exponential of minus j3 theta. This will become uh, sec cube theta m cos 3 theta plus 3 cos theta minus 3 gamma m sec theta m cos theta. So now if we arrange the term, then basically what will this term this cos theta term we can take it together. This will become gamma m exponential of minus j times 3 theta. So this will become cos 3 sec 3 sec q theta m cos of 3 theta plus this will become the cos theta terms we can take it together. So this will become 3 sec cube theta m minus 3 gamma m sec theta m and then cos theta. So if we equate the coefficient both sides, so the which is equals to this equation. So this 2 times gamma naught. So 2 times gamma naught will be equals to gamma m times, if we compare the terms, gamma m times sec cube theta m. So this basically n 2 times gamma 1 equals to 3 gamma m sec cube theta m minus sec theta m. So this is the two equation. Gamma m is given as 0.05 And so we can write this sec theta m, we can solve as cos hyperbolic 1 by n cos inverse hyperbolic ln zl by z naught divided by uh, 2 times gamma m, and this so if we plug in all the values of n, n gamma m zl z naught, so this will become cos hyperbolic of 1 by 3 cos uh, hyperbolic inverse cos hyperbolic inverse ln 150 by 75 divide by 2 times 0.05, and that basically sec theta m will be equals to 1.408, which will be equals to theta m equals to 44.7 degree. So we find this theta m from here. So now basically we can find the value of, now we know the theta m and gamma m are given. So basically now now we can just putting theta m, and then we can find 2 times gamma naught will be equals to this will become gamma m sec cube theta. So this 0.05 times sec cube theta is 1.408 whole cube, and then basically that you can gamma naught you can find as 0.0698. so this is gamma naught. And similarly we can put the value theta m value in second uh, this equation, and then basically we can find the gamma 1 as 3 gamma m sec cube theta m minus sec theta m. So basically gamma 1 will be equals to 0.1037. So with the symmetry problem, we can calculate gamma. Once we calculated the gamma one, gamma naught, other value we can just with the symmetry we can calculate just other values, like because this is the periodic and symmetric function. So the gamma 3 will be equals to gamma naught, and gamma 2 will be equals to gamma 1, which will be equals to 0.0698, and that will be equals to 0.1037. So now since we have find the gamma 1 and gamma naught, gamma 1, gamma 2, so then basically we can calculate the characteristic impedance for each of the lines. So this is for n equals to 0. The characteristic impedance is given as ln z1 equals to ln z naught plus 2 times gamma naught. So Z naught is given as 75 ohm, and this now we know the value of gamma naught, Z naught we know, so we can calculate ln Z1 equals to ln 75 plus 2 times 0.0698, and then basically that is equals to 4.457, and that basically once you take the antilog, and then Z1 will be equals to 86.3 ohm. So that is the value of Z1. Similarly, we can calculate uh, uh, that is the value of Z0 actually. So yeah, so that is the value of Z1. Similarly, for second and third line, we can calculate for n equals to 1 line, we can calculate characteristic impedance ln Z2 equals to ln Z1 plus 2 times gamma 1. So ln Z1 is given as ln 86.3 plus 2 times 0.101 gamma 1 is given as 1037 gamma 1 is 1037 so 1037, and then basically this Z2 we find as a 106.2 ohm. Similarly, n equals to 3, we can calculate ln Z3 equals to ln Z2 plus 2 times gamma 2. which will be equals to ln 106.2 plus 2 times gamma 2 is 0.1037. Then basically this will become 4.873. So Z3 will be equals to 130.7. So now basically you can see now as you can see from this uh, Z1 is nearly close to Z0, the 75 ohm resistance, and basically your like end line is nearly equals to your the load impedance, and basically so this is the design problem. You calculated all the Z1, Z2, Z3, and gamma 1, gamma 2, gamma 3, gamma naught, gamma 1, gamma 2, and then basically that is your design. Also, you can calculate the fractional bandwidth. So which is equals to the fractional bandwidth is equals to f by f naught, and f naught is given as 1 gigahertz. So this is equals to 2 minus 4 theta m by pi, which is equal to 2 minus 4 times 44.7 divided by 180, and then that will be equals to 1.01. So the fractional bandwidth delta f by f naught is equals to 101%. So that is your fractional bandwidth. So that basically define the designing the the uh, the Chebyshev impedance transformer design. So if you have any doubt, you can ask, or otherwise we'll move to next problem. Okay, so I think let's just move to next problem. So in this section, basically, so so a so in this section, basically, we need to find so this is a 50 ohm line, so which is connected to 100 ohm lines on both sides, and the length of these lines is 45 degree. So basically this problem is if we say like the uh, uh, so if we say uh, this line has the characteristic impedance parameter, which is S11. So scattering parameter S11 dash, S121 dash, S22 dash, which is, and this characteristics of the whole line, whole circuit we are defining as S11, S12, S21, S22. And then basically so this line is, so we can consider this a black box, and we can calculate the field, field in terms of this. So let's say this is this is the typical case of uh, reference plane transfer. So how the this is, let's say, two port network, and these are the input of the port, and these are, let's say, the reference plane of the this network. Now we need to connect this reference plane to other reference plane, which is 45-degree electrical length away from the this line, so this plane. So let's say this here the input port, here the parameters are A10, B10 at the source side. Similarly, here is A20. So here is A20, B20, right? So this is this is the reflected. Here this is the transmitted, and this is the reflected wave amplitude. So now we can here we can write this as A1 L1, and here we can write as B1 L1. Similarly, here also you can write, we can write A2 L1 and A2 L2. So this is length L2, this is length L1. So here also you can write B2 L2. So basically we need to find the relation of like the scattering parameters in terms of the this. So we need to find the, we can write S11. Then basically now we can write the we can write this. The S11 parameters of this network. We can write so. We can write the we can write this network. We can write the at B1 and L1. So basically, um, so we can write B1 uh, L1 equals to B1. So A1 L1. Uh, A1 B. No, no, just this we can write as a B1 L1, B2 L2 equals to S11, S12, S21, S22 equals to A1 L1, A2 L2. And we can the let's say this these are the network parameter for this small model, and the outer parameters are S11 uh, uh, S11 complement. So basically now we can write in terms of outer side parameter. So we can write as a so at the other port we can write as a B naught. So B10, B20 will be equals to S11 prime, S12 prime, S21 prime, S22 prime. So this will be equals to A10, A20, right? So then basically now we can write so if we move like let's say theta length away from this line, we can write B1 L1 in terms of A1. So we can write in terms of in terms of A1 naught. So we can write as a A1 L1 will be equals to, so this from here to here we are moving in the right direction. So exponential of minus theta terms we will take. So this will become A10 times exponential of minus uh, j theta 1. And similarly this side we are moving for B1. So we can write as a B1 L1 equals to, so we are moving opposite. So the reflected wave moves in this direction. So here we know the uh, yeah, so here we know the parameter. So we can calculate uh, in terms of that basically uh, in terms of like B1 naught. So basically that basically we can write a B1 naught exponential of minus plus j theta 1. Similarly, we can write as A2 equals to, so A2 equals to A2 of L2 equals to A2 of 0 exponential of minus j times theta 2. A2 B2 of L2 will be equals to B2 of 0 exponential of minus j times theta 2. So now basically we can substitute this. So basically now we can substitute uh, this A1 L1 and B1 L1s to this. Let's say this is the equation 1. So we can substitute in equation 1. Then basically we can write in terms of B naught. b naught b naught so we can write in terms of uh, 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 so we can write in terms of b naught b1 naught or b2 naught so basically like if you or you can just or you can write this also as a1 naught equals to exponential of so this you can write as a1 l1 exponential of j theta 1. Similarly a1 b1 naught you can write as a b1 l1 exponential of j theta 1. Similarly b2 naught you can write as a b2 l2 exponential of minus exponential no this is minus so b2 you can write a minus of j theta 2 and a2 not equals to will be equals to uh, a2l times exponential of j theta 2. So that you just take multiply by exponential of minus j theta 2 times, and then basically you can write in terms of that. So now if we write that, so basically if we take this, then basically we can just multiply by the uh, theta 1 and so we can multiply by this terms, and basically each row if we multiply by the exponential factors, then basically we can find b1 so we can find the b1 naught and b1 naught and b2 naught so we can find b1 naught b2 naught in terms of s1 s2. So this we can write as s11 exponential of minus j times 2 theta 1. S21 will be equals to exponential of minus j times theta 1 plus theta 2. This S12 exponential of minus j times theta 1 plus theta 2. And this will become S22 will be equals to exponential of minus j times 2 theta 2 times A10 B10. Similarly, we can write in terms of L1. So that basically, this, so we can compare the S11 parameter. So this, if we compare that S11 prime, S121 prime, S12 prime, S22 prime will be equals to S11 uh, exponential of minus j times 2 theta 1 s21 s12 exponential of minus j times theta 1 plus theta 2 s21 exponential of minus j times theta 1 plus theta 2 s22 exponential of minus j times 2 theta 2. So this is your s parameters in terms of that. So now similarly we can take transform also. If we just take conjugate, then like we can just interconvert between this, and if you like carefully adjust the parameter, then s11 s12 s21 s22 will be equals to s11 prime exponential of j theta 1 s21 prime exponential of j times theta 1 plus theta 2 S so this is S12, this is S21 prime exponential of j times theta 1 plus theta 2. This is 2 times. This is S 22 prime exponential of j times 2 theta 2. So this way also you can write. So now we need to calculate the S parameters of the inner network. So basically uh, that so basically inner network is our this. So this is the characteristic impedance Z, and that is our even network. So if we you can find the if you find the T parameters of this network, which is equal to 1 plus Z or 0 1, With this you conversion, you can find the S parameter from this, which will be equals to Z by Z naught divided by 2 plus Z by Z naught, comma 2 by Z plus 2 plus Z plus Z naught, and then basically it will be equals to 2 by 2 plus Z by Z naught, similarly this will be Z by Z naught divided by 2 plus Z by Z naught. So with this you can convert to that. So we know this theta 1 equals to the the value of the parameters. Theta 1 is equals to 45 degree, which is equals to beta L1. Theta 2 is also equals to the 45 degree, which is equals to the beta L2, and Z is given as 50 ohm, Z naught is given as 100 ohm, and then basically then if we know the s parameter, then basically we can find out the we can find out the so then basically we can write the S11 prime, S12 prime, S21 prime, S22 prime. So this 2 theta 2, so all the terms will be, so theta 1 1 plus theta 2 and 2 theta 2 will be same, and that will become like this exponential term will become minus j. So that basically this will become z by z naught. So this will become z by z naught minus j times. So this so if we put the value, then it will become uh, so now this will become, so this in terms of S11, this will become so in terms of S11, this will become exponential of minus j 2 theta 2. This will become minus j. So minus j times z naught is given as, we can take this as a zero point 0.5. So z by z naught will become zero point 0.5, and then it will become 2 plus zero point 0.5. This is minus, so minus 2j divided by 2 plus zero point 0.5 minus 2j divided by 2 plus zero point 0.5 minus j multiplied by zero point 0.5 divided by 2 plus zero point 0.5, and then basically this will become equals to uh, so this will become 2.5, so minus j times uh, 0 0.2 minus j times 0 0.8 minus j times 0 0.8 minus j times 0 0.2. So these are the S11 parameters for port 1 1 bar and 2 bar. So basically this is the answer for this. So that is so this was the second design problem. So basically we need to calculate the S11 parameters, which is matched to the line which is matched to two different kind of network, to transmission line which is connected to. So next let's just move to next problem. So then basically then like this so in this so if you have any doubt, you can ask. I will pause for some time and then we'll start the next problem. If you have any doubt in the previous problem, you can ask. Okay, so then basically let's just move to next problem. So then then we need to design a lossless T junction power divider which has a 75 ohm source impedance. So that is the 75 ohm source impedance. Uh, find the output characteristic impedance such that the input power is divided into 2:1 ratio. So basically, so we need to find what is the Z1 and Z2. So so basically, so input power, so we can write the input power in terms of input voltage. Then basically P in is equals to V in square by Z naught, right? Where Z naught is the source impedance, and which is Z naught is equals to 75 ohm. And now, now the uh, the output power at so if this is the characteristic impedance, so the output power uh, at port 2 will be equals to V in square divided by Z2, and P1 will be equals to V in square by Z1. So basically, now, so 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 the power is divided into 2:1 ratio. So this this P1 will be equals to 1 by third of P in. So so let's write as the so the so out so the total power P in, so the P in is equals to P1 plus P2, and we can write as a P2 as 2 times P1, P1 plus uh, 2 times P1, and then we can write as a P1 equals to 1 by 3 of P in. Similarly, we can write P2 as 2 by 3 of P in, or equals to P in minus P1, which will be equals to 2 by 3 of P in. So then basically the then we can write this P in we know. So this this P1 equals to so P1 equals to 1 by 3 of P in, which will be equals to 1 by 3 of V in square by Z naught. And P1 we know, we P1 is equals to V in square by Z1. So if we compare, then Z1 will be equals to 3 times Z naught. Similarly, we can write as P2 equals to 2 by 3 of P in, which will be equals to 2 by 3 of V in square divided by Z naught equals to V in square by Z2. So from here we can find this Z2 will be equals to 3 by 2 times Z naught, which will be equals to 1.5 times Z naught. So then basically, 3 times Z naught, it will become equals to 3 times 75, which will be equals to 225 ohm. And similarly, this 3 by Z naught will become 112.5 ohm. So that basically, we find, so now the impedance at the T junction, so basically uh, the impedance at the T junction will be equals to the impedance at Z in at the T junction will be equals to Z1 parallel Z2, and that if you take the ratio, this will become 75. So that means that the T junction, the source impedance is matched, and there will not be no reflection at the T junction. So that was the problem for problem that was the problem for like designing the power divider circuit or T junction kind of power divider circuit. So if you have any doubt, you can ask. Okay, so let's just move to next problem. So then basically in this we need to find what is the resonance frequency. Like we need to find the resonance. So this circuit is given, series RLC circuit is given, series resonator is given. So for this basically, so this so yeah. So for this basically we need to find the what is the value of R, L, and C. So R, L, C are given, and we need to find the resonance frequency F naught and unloaded quality factor Q unloaded and Q external loaded quality factor. And basically then basically also we need to yeah, so this we need to find, as we can see, like this is the series RLC circuit. So the resonance frequency F naught is given by 1 by 2 pi and square root of LC, which will be equals to 1 by 2 pi times L is given as 20 into 10 power minus 9 Henry, divide by C is given as 2 picofarad. So 2 into 10 power minus 12 farad. And then basically this will become this will become 1 by 2 pi times square root of 20, and this will become 40 times exponential of minus 3, and this will become 1 by 2 pi times 40, which will become now, no, this will become, so this is minus, this will become 21. So this will become 21, and this will become 4 into 10 power minus 20, it will become. Then if you take square root, then it will become 2 pi times 2 times 10 power minus 10. Then basically if you divide by 1 by 4 pi times 10 power 10, and this will become 10 by 4 pi times 10 power 10, which is equals to this will become to so now so this will become so this 10 power 9, and this will become 0.975 times 10 power 9. So 795.7 times 0.95, and this will be equals to 795 gigahertz, or this will be equals to 795.7 megahertz. This will be the resonance frequency F naught. And basically you can find the quality factors Q unloaded. So basically Q unloaded you can find at the omega naught L by R internal. So basically that is equals to so omega naught is given 2 pi times 0.7957 times 10 power 9. L is given as 20 nanohenry. So this is 20 10 power minus 9. And then this is R is given as 5 ohm. So basically here we need to take 5 ohm. So then basically it will become around 19.99. So then so basically also this this is the internal quality factor, and external quality factor we can write as omega naught L by RL. This is RS, which will also because RL equals to RS is there, so which will also will come out as a 19.99. And loaded quality factor QL will be equals to omega naught L by RS plus RL, which will be equals to omega naught L by RS plus RL. RS plus RL is 5 plus 5, which will be equals to 2 times 5. So half of omega naught L by RS or RL. So this will become 19.9, 19.99 divided by half or 2, and that will be equals to 10 points, 9.99 something it will become, roughly 10. So then basically this is the external quality factor. Uh, this is the internal quality factor. This is the external quality view. This is the loaded quality view. This is the unloaded quality. So basically, this way you can achieve the three quality factors for the series RLC network you can calculate. So that was the problem for designing that RLC network. So yeah. So with that, let's just move to next problem. So uh, so this basically we need to design a impedance matching network. So design a impedance matching network to match the ZL equals Z0 100 ohm to a load impedance of ZL, which is given as 200 plus J times 100. At 1 gigahertz, use the lumped element. So basically now we need to add, we need to design this like the combination of this LNC or LRC, so that this load impedance is matched to the input impedance. And basically like what is the then basically just we can we can uh, we need to find by the calculation by Smith chart. So let's say ZL is given as ZL is given as, let me take it as 200 plus J times 100 minus J times 100, and Z naught is given as 100. So then basically we can find the normalized impedance ZL by Z naught. Let's say it's called small ZL, that will be equals to 2 minus J times 1. Similarly, we can calculate this is in terms of impedance, and load admittance YL we can calculate as 1 by ZL, which will be equals to 1 by 2 minus J times 1, which will be equals to so this will be equals to 2 plus J times 1 divided by uh, 2 plus minus J times 1 multiplied by 2 plus J times 1, which will be equals to 2 plus J times 1 divided by um, so this will be will become so that basically it will become that it will become 2 square 4 plus minus j square plus multiply by 1, which will be equal to 5, and this will become zero point 0.4 plus j times zero point 0.2. So this is the load admittance. So now this is the load admittance. Let's see how we can just find the matching network with the so with the uh, with the uh, with the so with the uh, with the Smith chart. So then basically we can see on the Smith chart. See, so this is the Smith chart. So first is the Smith chart. So then if you are so let's say if you like if you want to locate this point, so where you will locate. So if we are using ZL, so this is ZL is 2 times 2 minus J times 1. So if we note that like there, so so this is the 2, this is the 2 point, and minus j times 1. So this the admittance is chart. This bottom side is minus minus point 0.1. So the if you move this side, it's minus reactance is negative, and this side reactance is positive. For admittance side, this side reactance is negative, this side reactance is positive. And if you are if you are moving along the constant resistance circle, so basically if you are moving in this direction, clockwise direction, then basically you are adding the inductance in series. Or if you are moving in this direction, then basically you are adding capacitance in series. Also, like if you are on the admittance circle, if you are moving so this so in this chart basically both the circles are given. So then basically you can like so let's just plot our point which we calculated. So let's just plot in terms of z minus. So this is the 2 point, so this is the real axis, and minus j point 1, so we need to move downward. So this is this line, so this is point, this point is point 1. So if we see like where this line goes, then basically this is the point 1. So this is our point 1. Similarly, as you can see the admittance circle, this point correspond to the point 0.5 reactance actually. So this correspond to point 0.5 admittance, which we so this will correspond to the this will correspond to just wait. Huh. So this will correspond to this point one point one this will correspond to the point one reactance, and that basically that basically, and for this is given for uh, this is given for, so this point is given. So now let's just draw the circle. So basically this is our load point. So that basically you just find from the admittance circle. So that basically now you can write you can write as this, so in terms of admittance you can write as, so just so then basically like now you need to match this line. So basically like this is so if we draw the 50 ohm circle, so basically let me take a different color. So this circle is 50 ohm circle. This circle is 50 ohm circle, and if we draw the admittance circle around this, so this is the admittance circle. So let me mark with the green color. So this is the admittance circle correspond passing through our load. So now basically we need to we need to so we can match in two ways. So one we go through two paths are there. So one one matching thing, one matching network we can design by this. So we go from this path to here, and then this path to here. So finally we need to match to the central point. So basically now to match this, so basically then we need to we will so in the admittance circle we are moving in the positive direction. So basically we are adding so if we are moving into positive direction, this side is negative. So we are adding capacitance in front, and if you are moving in this direction, then we are moving inductance in front. So basically, we can define in two ways. Like we can design the network in two ways. First, add so this we are moving in the constant admittance circle. Then we will move to constant resistance circle. So basically, once we add the capacitance on inductance in shunt, then we will add the capacitance or inductance in series actually. Once we are moving in constant resistance circle. So that basically with the this let's just so then basically let's just so for this is given as this is given as yv is given as zero point 0.4 plus j times zero point 0.5. So yb is given as just wait. So normalized admittance. Uh, so this will correspond to 0.5. Yeah. So now we need to find this point. So basically, we will move like we need to find what is the admittance correspond to this point. So this point is given as zero point 0.5. So the reactance is zero point 0.5, and the admittance is also zero point 0.5. So this admittance is zero point 0.4. Just wait. Hmm, I think something wrong. 2.0 should correspond to uh, 2.0 correspond to 2.0 correspond to yeah. So then basically so this point correspond to the conductance. Huh. So basically, like if we find the normalized, the normalized y naught will be equals to y naught will be equals to the 1 by z naught, which is equals to 1 by 100, which will be equals to the 0.01. So basically, now that basically we can find the yl is equals to 1 by zl, and zl is given as zl is given as 200 minus j times 100. So this is given as 200. So 1 by 200 minus j times 100. Then basically we can just take common 100, and this is 1 upon 2 minus j1. This will become uh, so this will become 2 plus j1 divided by 100 uh, uh, times 2 square plus 1 square, which will be equals to 5. So 2 plus j1 divide by uh, so this divide by uh, this is 100 into 5. So that basically, and we can just divide yl. Uh, no, small yl we can write as yl divided by 100 yl y naught. This is equals to so the yl is 2 plus j1 times 100 by 5 divided by 0.01, and this will become 2 plus j1 divided by 5, which will be equals to zero point 0.4. So this will become zero point 0.4 plus j times zero point 0.2. That is your normalized admittance. So that also in this way also the same. So basically uh, now basically for this point at the this circle is basically equals to the uh, zero point 0.5 conductance. So basically this this point corresponds to zero point 0.5 plus j times zero point 0.5. Just wait, I think something wrong. So this B point is basically 0.4, 0.4 times 2 plus 2 times 2 plus 0.1 plus 1. Yeah, so this will become uh, zero point 0.5 zero point 0.5 plus j times zero point 0.5. These points correspond to. So the y of b is equals to zero point 0.5 plus j times zero point 0.5, and basically like now equals to yl plus j times yb, so plus j times b, which will be equals to so then basically yl we know the yl is basically equals to yl is basically equals to uh, 0.4 plus j times zero point 0.2 plus j times b. So j times so this j, b plus zero point 0.2 equals to 0.5, and b equals to your, so j times b will be equals to 0.3. So that basically j times b by z naught will be equals to uh, j times so basically that will be equals to uh, so this so basically in this path, so if you are moving in this direction, so basically then you add a capacitance in shunt. So basically that will be equals to j times omega c1, and once you calculate the c1, c1 will be equals to 0.46 picofarad. So that will be your this point. So this 0.46 picofarad capacitance in shunt. Now you have reached to this point. So now you have reached to this point. Now you need to move along the constant a resistance circle. So basically now you need to add the either capacitance or inductance in series. So basically now you are at this point. So this is basically uh, zero point 0.5 plus j times zero point 0.5 circle. So that basically now you need to add the resistance. Basically this final point is this zero point 0.5 plus j times 0. So basically you need to add you need to this the the impedance of this point. So basically like you need to add the series so then basically if you calculate the impedance of this point, so basically the impedance so yb point the admittance is zero point 0.5 plus j times zero point 0.5, and then you can just calculate the impedance at b point, which will be equal to zero point 0.5 so 1 by zero point 0.5 1 plus j, and this will be equals to uh, 1 minus j divided by zero point 0.5 multiplied by 2, and which will be equals to 1 minus j. So this is equals to the this is equals to this. This is basically your. So now basically you need to add the inductance that you move to this point. So basically, so now with the I made a mistake. So basically, our point will be I can got confused. Yeah. So our point will be this. So our point will be not this point. So this is, let's say, this is the final z equals to one circle. So we need to find this. So our if this is 2 times 1.0. So 2 point is this one, and 1.0 is a capacitance is this one. So that basically 2 minus so the negative side is minus. So this is our load point. So this is our ZL or YL. So this corresponds to, as you can see, this corresponds to zero point 0.4 times conductance. Also, this corresponds to zero point 0.4 plus J times zero point 0.2. So this is yeah. So now earlier it was not matching because I made a mistake in the plotting. So basically, like if you plot this at the constant resistance circle, this is correspond to 2 minus J times 1. So this 2 is the this resistance, and J times 1 is the corresponds to this line. Also, you can point the to other direction. So that basically in this the admittance value is zero point 0.4. So as we can calculate it, this zero point 0.4 plus j times zero point 0.2. So this zero point 0.4 is this one, and we need to and at the admittance positive side means we need to move downward. So then basically zero point 0.2, this is the zero point 0.2. So then basically just uh, then basically you are at this point. So this correspond to zero point 0.4. So YL equals to zero point 0.4 plus J times zero point 0.2. So this point correspond to zero point 0.4 plus J times zero point 0.2. Now, if we move along the constant admittance circle, so this we will move along this line. So this is line, and this will intersect here. So basically, what we need to do, we need to add a load impedance. So we need to add a uh, shunt conductance in this, and then series in this direction, or we can design by this. So from this to this, we will add a shunt capacitance or inductance, and then series capacitance or inductance. So basically, we can move by the two path. So now basically we find that the uh, the shunt capacitance basically we find at 0.46 picofarad. So now with this, so basically from here, so from here if we see like how much, so this point if you see like if you see this is the correspond to 1.2 inductance circle. So we basically, so this point correspond to, so this point corresponds to the one. So this point corresponds to 1 point. So 1 plus j times 1.2. So this point corresponds to this point corresponds to, so if we extend this and this point corresponds to 1.2 times, uh, 1.2 times, this is 1, this is zero point 0.9. So this is zero point 0.9. So basically that basically equals to the yeah. So this is the yeah. So this corresponds to 1, and the value corresponds to this will be around 1.1. So this value will be around some 1.1, between, it will be equals to between 1.2 and 1.3. So the series capacitance basically it will be equals to 1.1, 1.1, or 1.2 it will correspond to. So then basically your you need to add. So we are moving in this direction, so in the clockwise, so you need to add the the zb point is 1 minus j times 1.2 point. So you need to add plus 1 point j times 1.2 point to get zb equals to 1. So z equals to 1.2, so this will corresponds to j times x z naught equals to j times omega L1. L1 you will find x times, so x times z naught by omega, which will be equals to around 19.4 nanohenry. So if you see design this network, so this network will look like this series inductance, also the shunt capacitance. So that will match to this load, and this load will match to this impedance for this series. So this is L1, this is C1. So that basically that input impedance will be 100 ohm. Also, you can design other path. So if you move from, also you can go to other path. So this points. So let's just say, uh, so this is our so YL is our zero point 0.4 plus J times zero point 0.2. Now let's say A, this is A point. So what is the YA, which will be equals to the, this is our zero point 0.4, zero point 0.4. So this is this above side is minus. So this is equals to zero point 0.4 minus J times zero point 0.5, right? So then basically, so this is Z naught minus J times zero point 0.5. So yeah, so this is yeah, this will correspond to around Z naught plus J times zero point 0.5. And then basically to get this from, YA will be equals to YL plus J times B. And then basically you can calculate basically, so YL is 0 0.4 plus J times 0 0.2 plus J times B. So J times zero point 0.2 plus B equals to J minus J times zero point 0.5, and B plus zero point 0.2 will be equals to minus zero point 0.5, and B will be equals to minus point, J times B will be equals to minus 0.7. So basically now we can equate J times B by Z naught equals to minus, so this will be equals to minus J omega L1. So minus J omega, so this 1 by omega L1 j minus j by omega L1, and this L2 L1 you will get 23.05 nanohenry. Now you are at the A point. To move, so corresponds to A point, your your inductance is 1.2. So basically you need to add 1.2 back the capacitance. So basically you need to move in the other direction uh, for uh, for this. Then basically you need to add a series capacitance actually. So this that you just calculate this by like this j times this is minus j times 1.2 and this you can calculate this is 1.3.0 1 point so the capacitance will be equals to c equals to 1.1305 picofarad. So that basically so if you design in other ways, then this your you add a shunt inductance, so your inductance will be in shunt, and then your capacitance will be in series with the load resistance, and which will be equals to the this is 23.05 nano henry, and this other one is 1.305 picofarad. So this is your impedance matching network, and basically with this you can just design an any impedance. So pardon on my side, I just initial point I just marked it wrong, and that's why this each side value were not matching. And like later I corrected, and then we are getting the correct values. So that basically you can use this impedance admittance Smith chart to design the any of your impedance matching circle and impedance matching network, and basically that you can use to use for your you can use for just to match any impedance or any load to the any load to a transmission line or coaxial cable. So this was the probably last problem for today. So you can try solving this problem, and this Smith chart you can just download from web. I just download from this site. So Smith chart in color. So this one has both admittance and it's in impedance Smith chart at the source and load. So basically both impedance and admittance Smith chart, and basically that you can download and just you can like if you have any handwriting tool, then basically you can just have the like have you can match any like load any types of load to any of the you can design any impedance matching network with the Smith. So uh, that was the last problem from my side. If you have any doubt, then we can discuss that doubt, or otherwise we can have or we can end this session if you don't have any other doubt. So till then, thank you so much for listening this session. So I would be I would be happy to take any. I will pause for a while. If you have any doubt, then just let me know. Otherwise, just end this session. Okay, if you don't have any doubt, then let's just end this session. So thank you so much for listening this session. We will meet this Tuesday in the regular session. Till then, thank you. So if you have any doubt just before the exam, let me know. Let me know the uh, your doubts in next class. And in this class, basically, let me summarize. This class, we solved some of the problems like design problems, basically uh, for the content covered in this previous 6 or 7 sessions. And then basically, we covered those sessions. And also, this we can just so if you have that basically we just covered mainly the design problem compared to the regular problem which we solve are typically objective type of problems, but in this we try to solve more kind of design or subjective types of problem. So that basically, I hope there is a clarity with the Smith chart. It's a very powerful. It's a typical engineering kind of technique and very powerful. It's still used in like these days. It's invented and long back, but it's still relevant in this way. There is no alternate to this. So even lot of automated things are has come, but those analyze in terms of Smith chart only. So this is a very powerful mathematical technique, and once you get feel of it, then it's very easy actually. People find it very complicated, but it's very easy technique. So then basically I leave you with this, so you can download any Smith chart, and you can just on some tablet or those or pen and paper, you can take print out of the chart, and you can uh, just solve like impedance matching problems on that Smith chart. So till then, thank you so much for listening these sessions. I wish you a great learning. If you don't have any doubts, we can end this session, and we will meet next time in the Tuesday session. Uh, Bye. Have a great time. Thank you so much.